Hi everybody, welcome to our lecture today about network fundamentals. As we start our discussion about networks, we're going to talk about how they are impacted and used by the Unix environment. So let's jump right into IPC via network communication. So IPC is inter-process communication. What this is talking about is how two different processes can communicate. And in this case, we're talking about communication via networks. So some of the terminology we're going to use here is going to be a client-server architecture. That means we've got some sort of arrangement where one of the processes is known as the server, and its job is to continuously wait for other connections that come in. And those other connections that come in will be from processes that we'll call clients. So the server is always running, and it's always waiting for new connections to arrive. That's its job. It stays running forever, or at least until the thing gets shut down. The clients are transient. They come, they go, they request a service, they request a file, and then they disconnect. Some long-running clients certainly can stay connected, but for the most part, the server exists to do what is asked of it whenever that request comes in. As an example, a web server is a classic server type. The web server is always looking for new connections, new requests for the web files that are stored on it. And the web server doesn't know how many clients are going to connect. It doesn't know how many clients are going to connect at any one time. They could be of lots of different browser types, so Chrome or Edge or even Lynx, the old school all command line, all text-based web browser, Lynx. So in the Unix world, we have the concept of a daemon, and a daemon is a type of server. It's essentially a process that's running in the background, which we've talked about those before. And these daemons are ready to provide service to the programs that need them. So here's a few sample ones. For example, the syslog d daemon is for the system log, and it maintains the system log. It keeps it updated with what's happening on the computer on that server, the physical hardware server. The LP daemon, the line printer daemon, is for print spooling. NTP is the network time protocol managed by NTPD, that particular program that worries about is the clock on the server synchronized to network time, which hopefully is connected to the real time that the whole internet is using. DHCP-D, that is for assigning TCP IP addresses to network clients that request it. And we'll talk more about TCP IP as we get through the lecture today. In Unix, daemons all have the init process as their parent, or at least the official daemons that are started up by the system when it is booted. They will all have init as their parent. Init starts at the process ID of 1. One interesting change in just the last year has been the surge of systems that have replaced classic init with systemd, which is a much larger set of software. Systemd can do a lot more than init does, but the purists, those that want to stay with init, don't like it because it's so large. It does so much. It kind of flies against the standard Unix traditions of having lots of small interconnected pieces that all work together. Systemd instead is a monolithic, large, some would say bloated piece of software that, while it does a better job, is not as open or as changeable or as modifiable for hobbyists that are messing with systems. For an example protocol, let's take a look at this. So a server exists to field requests that come in. Clients send those requests in. They communicate via a protocol. In this case, the HTTP protocol stands for Hypertext Transfer Protocol. It's very simple. All it does is it supports this one feature, which is getting the file that's requested. They'll give me a file, I want to download that file. It's very standardized. It tells us exactly how the client requests are going to come in, tells us exactly how the server is going to respond, and it's entirely text-based, which is really handy. All the requests, all the responses, all the errors, everything is text-based. The most widely used web server software in the world is Apache. And HTTPD is the name of the Apache daemon that is running all the time. But don't confuse the name of that daemon, HTTPD, with the HTTP protocol that the daemon supports. So as we look at HTTP here, it has two primary modes of interaction. In the first mode, it's a very simple mode. You simply pass it a text-based command that says get and then the file name. So in the example we have here, abc.html, we're just saying, give me this file. Then the server is going to get it, and it's going to return that file that you've requested. There's an enhanced mode where you can specify which version of HTTP you're using, 1.0, 1.1, and there's always different ones that they're talking about, but they tend to be, HTTP tends to be a fairly slow-moving standard because it holds so much of the internet together. In the extended mode here, the enhanced request mode, it's going to respond with some header information, such as what kind of server is this? Give me the version numbers of the software the server is running. And then eventually we'll get the data file after a blank line. So this is just a way to get more information out of the system. For debugging some of these text protocols, for example HTTP, we can use a tool called Telnet. And it was originally designed, Telnet was originally designed to interact with our text-based command line session. So when we would SSH into a server, in the old days we would use Telnet. The problem with Telnet is that everything is passed around in plain text, all of the usernames, all the passwords, so it's really hard to keep anything secure. So nowadays SSH will secure the connection before data is sent back and forth in a plain text manner. So it is the current standard, and almost without exception now, Telnet is not only unusable, but it is blocked. It doesn't even exist on those systems. One of the key points about Telnet here, and SSH as well, is that you can specify the port that we're going to connect to. And the port will help us identify which process on the server we want to talk to. More about ports in our next lecture. Let's do a little demonstration here of Telnet. I'm going to grab my little command line prompt and bring it over to the other screen. So here on our prompt, we are going to make a Telnet connection to EECS. So telnet eecs.oregonstate.edu on port 80. That's the typical web port. Then I'm going to hit return. This is now the web server, and I can type commands to the web server. I'm going to type get /, which means give me the file at the root of the directory, and I want I'm going to use version 1.1 here, so this is my /1.1. This is my extended version, my enhanced request mode. Hit return. Type in host eecs.oregonstate.edu. Enter and enter again, and there is the HTML page returned directly to me. So as a text command, as a text-based protocol, I can interact with that protocol with direct test that I type in with Telnet. Okay, so a non-text-based application protocol, the reason for doing those is that so let's look at it from the perspective of text-based protocols. So the text-based protocols are very easy to debug because you can see the text that's there. They're easy to teach, they're easy to understand, we can write them down, we can print them out, they're very simple. But the disadvantages is that it's not compact at all. So we are using entire bytes we're using a byte per character to transfer these things around. So we can compact a lot more data into it if we were doing this in a simpler manner, such as binary, hexadecimal, anything with compression, just some way to be able to transfer the commands in a more efficient manner. And so our server is going to have to spend a lot of time just even parsing all of this text, this XML text that we're sending back and forth here. And we want our server to be doing more interesting things than just parsing text. Okay, so the systems that we use to connect to each other across this network, we can talk about the different technologies involved here in the sense of it being layered together. So this is one of the classic methods of describing and teaching networks, and if you take the networking course here at OSU, you'll become a lot more familiar with this particular model. But let's go through it here too. So there are 5 primary models from the way that we describe our network layers here. Our model consists of 5 layers. So our top one is going to be the application layer. The application layer is our software. It's what we're doing. Our software is what is going to use the network for some particular purpose. And it doesn't care about how the data gets from one place to the other. All it knows is that it is requesting information and getting it. So a web browser, a game, chat clients, email, all that is just It's just programs that are being run that use the network. From the perspective of writing network sockets in C, which is how we are going to interface with the API, that's our primary API to interface with this network, we would use send and receive, the C functions. Going down a level here, transport, the fourth layer. Transport deals with the protocols that control how data gets from one host all the way across to the other. And it doesn't matter how many nodes or hops or networks the data gets through, the transport layer deals with the entire connection path. And there are two primary ways that it's going to get data from point A to point B. There's more, but these are the two primary ones that are used. TCP, Transmission Control Protocol, is connection oriented, which means that both sides establish the connection and then use it. It has guaranteed transport of the data and guarantees that the data will be arriving in the same order that it was sent. We'll talk more about this in a bit. UDP, on the other hand, is the Universal Datagram Protocol, which was before TCP was developed. UDP was the one in use, and it's connectionless. The packets are just blasted across the network, and there's no guarantee about practically anything. Okay, so the network layer, this is where IP lives, and IP is used to name an address and handle the routing from host to host and across the networks. So the addressing and the organization of that set of connected hosts is defined by IP, by the Internet Protocol. And we're still independent of the actual physical connection type at this point. We're merely talking about the addressing that's being used across all the devices on the network, while transport deals with getting the bits from place to place. The link layer is designed for, its purpose is to get data from just one node to the next neighboring node. So from, say, my computer to the switch that it's connected to, or from one phone with a Wi-Fi connection to the wireless access point. Just the connection between those two devices. The Ethernet is our de facto method for addressing and signaling across whatever type of network we're talking about, whatever type of physical connection we're talking about. And it's going to use something called media access control to communicate with IP. They work pretty closely together. So the link layer, again, is just for that direct connection between two devices, and it controls how they signal and talk to each other. 802.11 is the standard that is the Wi-Fi standard, and it's our de facto protocol for wireless communication. So there are certainly other protocols for sending data from point to point, but the two most common by far are Ethernet and 802.11. 802.11 does some fantastic tricks and magic for dealing with extremely congested transmission space. Everybody's trying to send radio signals at the same time, and 802.11 controls how that works. Alright, and then our last layer, layer 1, is the physical layer. So this is the actual hardware that connects our two hosts together. From a copper perspective, we're talking about Cat5, Cat6 network cables. And that is going to connect most of the world together. We can have long-haul connections that are fiber optic, but anything short is going to be done in copper. So a typical stranded network cable is going to have a maximum transmission distance of 10 meters, while a solid core network cable, so 8 solid copper wires in that thing, can go about 100 meters per the standard. Radio is, of course, how we would enable wireless devices to communicate, but that also occupies the physical layer of our model here. Okay, so TCP, from the high level, the combination of TCP and IP provides communication between the two processes, and they might be separated by the network. We can still use TCP and IP to communicate on the same host using these network principles, using these network APIs. So that's why we can say that it's potentially separated by an actual network. So a TCP/IP is Transmission Control Protocol and the Internet Protocol. TCP is the protocol that your application interacts with. So every layer can interact with the layers above and below it. So in the sense of TCP, let me backspace here a bit. In TCP, our application talks to TCP to handle the connection. and TCP then relays information to IP to make sure it knows where things are on the network. Details. So TCP is the most commonly used protocol for getting information back and forth. It's far more common than UDP is. TCP is a byte stream interface, just like the standard I/O library that we've been using this whole course. So byte stream is going to be, put in a few bytes, read a few bytes out from the other end. It's connection oriented, so both sides establish this connection and then maintain it, which takes resources to keep that connection open until the two sides explicitly close it, or in the case of a timeout, they'll disconnect if no data is transferred over too long of a time. TCP connections are bidirectional. You can send data either way through the sockets that are established. And it has some really fancy controls that slow the connection down if there are any nodes in the path that are really burdened with traffic. It can tell that. It can see that there might be loss on the network. Maybe there's a lightning storm in the area and it's causing interference on the line. TCP can detect that there are slowdowns in the traffic and will instead handle the connections in such a way to slow down the rate of transmission to make sure that the data gets where it needs to go. So our applications are built on top of TCP/IP. TCP/IP is going to pass the bytes between the processes, but it does not interpret those bytes. You write the application protocol on top of TCP/IP, and that is going to define what the bytes actually mean. That's what your program does with those bytes that it's sending and receiving. So we can think of TCP/IP like a phone connection. The phone is what actually transfers the sound between two people, but it doesn't do any interpretation of the meaning of that sound. So a possible telephone application protocol, in this case Bob calling Alice, and Alice does not look pleased to hear from Bob, but Bob calls Alice, Alice answers and says hello, and then Bob says hi back, and they both start exchanging information. It's kind of a three-way handshake to establish that phone call. TCP/IP starts the same way. We have a client and we have a server, and this is kind of a technical diagram that shows the type of packets that are being sent back and forth. The client will start in a closed state, and so will the server. The client will send out a packet called a SYN packet, S-Y-N, for synchronize. A SYN packet hits the server, and the server sees it and replies back with a SYN packet and an acknowledge packet. Those fly over to the client. Then the client responds with an ACK packet, short for acknowledge. And once it's sent that acknowledge packet, it will also start to send data, and then they're off to the races. They start communicating back and forth. So to compare the two here, TCP sends out the network traffic. It's going to be organized in bundles called packets, and it's going to use the addresses that it gets from IP. IP, however, does not guarantee anything. IP does not guarantee the data integrity, meaning that the contents of the data that arrive are what was sent in the first place. IP doesn't guarantee packet order. IP doesn't guarantee that there won't be duplicates, and it won't even guarantee that the packet will arrive, because IP is just addresses. That's all it is. You can think of it like being the numbers on houses on a street. That's IP. It's up to the post office personnel who are driving and managing where those letters go in the post offices to figure out whether or not they're sending the letters in the first place to the right addresses. That's TCP. TCP can detect if the integrity of the stream of packets encounters issues, and then it'll do things to manage that, such as reordering them or even requesting a retransmission. If too many packets come in that are all duplicates, it'll drop those, and that can happen by buggy or devices that are overloaded somewhere on the system or somewhere on the path from point A to point B. You might have a switch that is duplicating packets, or it sent out one particular branch and then is assumed that it's dropped, so it sends it out again along a different branch, but then the first one actually arrives anyway. That can cause duplication. TCP knows how to clean up those kinds of things before it delivers the data back up to the application. Okay, so UDP. UDP is totally different. It's connectionless. There's no handshaking. They don't communicate. They don't talk to each other about talking to each other. They just start talking. The data is broken up into packets that are instead called datagrams. And the server does not remember clients between the datagrams. They could be dropped by the network, they could arrive out of order, their contents might be messed up. So UDP has a lot less overhead than TCP, and because of that, it's much faster, it's much more efficient to transfer data. So when would we use UDP? Well, we would use it for when we're streaming video or audio. We don't really care if a frame here or there gets dropped. Maybe we're playing a game of some kind, and maybe a packet after one packet at a 20, maybe it doesn't matter all that much. Maybe we're broadcasting to a million people at once on YouTube in a live stream. Doing that kind of thing, we don't want to establish a connection with each one of those clients. We just want to send the data out there, and whether or not they can receive it, that's up to them. So that's UDP. Let's talk about the Internet Protocol a little bit here, some details on it. So IP specifies how we address the machines on the network. And if that machine that we're addressing is not on the same local network, then IP is going to dictate how the data can be routed to it. So that's this organizational addressing that is built up by IP. So every network interface, which is a fancy term for the network card, the network jack, on the back of the computer, that has an IP address. Every interface gets an address. And that address has to be unique on the network, specifically on the local subnet for that network. And you'll talk more about subnets in the networking course. An IP version 4 address, which are the classic ones you're used to dealing with, they are 32-bit binary numbers. They're usually represented, though, in a dotted form, so as 4 1-byte decimal numbers, because this is a lot easier. 223.1.1.1 is a lot easier to remember and to say than this whole binary sequence at the bottom here. That's not what we want to be trying to communicate. So our interface is the connection between, say, our computer, a host or a router, and that physical link. That's the jack, right? So a router has multiple interfaces. A switch has multiple interfaces. A host, so a computer, an end node, typically is only going to have one, maybe two if it's a really fancy server that has redundant connections, or maybe it does have a connection onto multiple networks at once. So wired Ethernet, wireless 802.11, those are going to be the interfaces that are on that computer. Typically, computers are going to have one Wi-Fi card that they'll use to communicate with some wireless access point. So remember that every interface has its own IP address. So devices that have more than one interface control multiple addresses. So let's look at this example over here. This example here has a router in the middle. And this router is controlling 3 different subnets. And the subnets are these blue amorphous clouds. And just for now, think about subnets as networks, as local area networks that enable these computers to talk to each other. The router manages the connection between each of the 3 networks. If you look at these addresses that each of these computers have, the first 3 parts of this dotted quad are all the same. 223.1.1. It's the same for all 3 of these. That means they're all on the same subnet. And that assumption can hold as long as we say that anything to the left, so these first 3 things, as long as those are all the same, and we're going to define that as our subnet, then the last number on the right side has to change for each individual host. Now, in the old days, we would call this a Class C network or a Class C address, which means that only the last quad to the right is changing. Nowadays, we use something called classless internet or interface domain routing, which means that we can change where the actual split is between the subnet on the left and the actual host identifying bits on the right. But for now, just think about it as the last part here is the part that changes for the individual computers. So here's our 223.1.1 network, and we have computers 1, 2, and 3. And the router, in order to communicate, also has to have an address. So it also has an address at 223.1.1, and in this case, it's on point 4. Over here is our .2 network, 223.1.2. Here's devices 1, 2, and then the router is on 9, so it can communicate over there. And finally, our subnet number 3, 223.1.3. The router is at 27. This host is at 1. This host is at 2. The router can communicate through any of its 3 interfaces to link these subnets together, but has to have a foot on each as a separate address. Let's talk about the difference between IPv4 versus IP version 6. So IP version 4 uses 32-bit addresses and therefore has 2 to the 32nd possibilities, 2 to the 32nd unique addresses. That's 4 times 10 to the ninth, which is about 4.2 billion addresses. That sounds like a lot of addresses, and it is. The problem is that it's not enough for the world. So in my house, for example, I've got an Xbox One, a 360, at least 5 computers, a bunch of cell phones, amps, Blu-ray players, printers, even 3D printers these days, and watches. They all want to have IP addresses. They want to consume these. A lot of these can be handled by the routers, in the sense that we can use the router to create our own internal, private, local area network. And our addresses will be hidden from the outside networks. We can define as many addresses, an unlimited number of addresses that we want inside our own network. So up in this little picture in the corner here, we can think of the router as being a gateway where it has one address on the outside that it uses to talk to the IP, or that it uses to talk to the internet. That's the address that it's known by on the internet, but internally it can have an unlimited number of addresses inside that it defines different networks on, and we can connect routers to routers to routers to make however complicated a network we want. This is how OSU works. This is how all large companies work that have to have lots of internal IP addresses, but only, say, a handful of external IP addresses. So the router acts as the bridge between the local area networks, the LANs, and the wide area network, the WAN, which in this case is represented by the internet. Okay, so the fact that we can do that with a router, though, shines light on the problem. We're saying here there aren't enough addresses to go around, so you have to come up with some system where internally you can define your own addresses, because there are no more to give out for the wide internet by itself. Other things that are putting pressure on the address space these days would be the Internet of Things. That's what's saying, hey, my left cufflink is going to talk to my tie via my right cufflink, because everything has to have a address and a device on it these days. So having Internet of Things everywhere means we don't have near enough addresses. Besides, all of them want to stay on. We want to have always on connections everywhere. We also have some inefficient address allocation going on. So in the old days, gigantic blocks of IP addresses were given out when we thought that we had an unlimited number of them, especially when we were talking about the internet still as a research entity, a research device. Alright, here we can see the display of who has the most IP addresses on the internet. And the United States military has 12/8 blocks. Each /8 block is 16 million IP addresses. So the U.S. military has 8 of those things, and so it's got around 201 million addresses. So level 3 communications, which is one of the big internet backbones, has 2/8s. HP, one early day tech company, has 2 of those. And we see that same pattern for a few of these other early day computer companies. Here's Apple, here's IBM, all kinds of different stuff. Some of the old companies in the United States also have a lot of these addresses. So Ford, the Ford Motor Company, for example, has 16 million public IP addresses. Strange. Halliburton is on here. All kinds of different stuff. Even some stuff associated with some countries and aspects of governments outside of the United States are represented in the internet. Here we can see the Department of Social Security of the United Kingdom is in here with 16 million. The Ministry of Defense for the UK is on there too. Even the Post Office has 16 million addresses. And that's not really very efficient usage of public addresses. So IPv4 versus 6. IPv6 uses 128-bit addresses. So since we're talking about exponents here, the difference between 2 to the 32nd and 2 to the 128th is enormous. Far bigger than just 128 minus 32 would have you believe. So 3.4 times 10 to the 38th is much bigger than 4.2 times 10 to the 9th. What it breaks down to 50 octillion addresses for each of 6.5 billion people on Earth. That is a lot of addresses. So theoretically, a lot of these addresses are actually reserved for some special purposes. So you can think about this as being cut in half, essentially. A lot of that is used for research, a lot of it is used for testing and loop back and all kinds of different things. So call it half. All right, so each of us only gets 25 octillion addresses. So maybe every square inch in everything you've ever touched your entire life, isn't going to put a dent in the number of addresses that you have available to you. So back to just our process. To conclude here, a process can use just one interface to communicate with itself and other processes on the same machine. And it does that by referencing its own interface's IP address. So when it sends data out, it doesn't send it out to some external address, it sends the data to its own interface. And it can also do the same thing by referring to a special host name called localhost. And we can indicate which process that our process is talking to by specifying the port. Every process can be listening on a particular port, and we can control which process we want to talk to by varying the port, by changing what's there. All right, I hope this was instructive, that we were able to learn something about some of the fundamentals of network architecture. And in our next lecture, we will be talking about how clients connect, and we'll see some C code involved with that. Thanks, and we'll see you next time.